Welcome everyone in lecture number 31. In this lecture, I will introduce about finite Fourier sine transform. In my last lectures, I have discussed about infinite Fourier sine and cosine transforms, where the interval of the given function was from 0 to infinity. And it is supposed that function is defined there and it is piecewise continuous in that interval, and also satisfies Dirichlet conditions. We use finite Fourier sine transform when the interval of the given function is finite, and it also satisfies Dirichlet conditions in that finite interval. So let we are given a function fx. Let we are given a function fx which is defined in intervals say 0 to L, where L is any finite number, and it also satisfies Dirichlet conditions. I have told you about Dirichlet conditions. Okay. And in this interval, obviously. So we define the finite Fourier sine transform of the function fx in this interval, and we denote this by fs of fx. We always use the word finite before Fourier sine transform whenever we talk about finite Fourier sine transform. If we simply say Fourier sine transform, that means that it is infinite Fourier sine transform. Okay. So it is denoted by fs of fx. It means we are talking about finite Fourier sine transform of the function fx. And it is defined as integration 0 to L fx sine p pi x divided by L dx. The obtained function will be the function of p, and it is denoted by fsp. Sometimes we also denote this expression by fs bar p, because the obtained function is the function of p. That's why we have used p here. So if we are given the interval say 0 to pi, in place of L, we are given say interval 0 to pi. In that case, Fourier sine transform, finite Fourier sine transform of the function fx is defined as integration 0 to pi. In place of L, we have pi now, and here we have fx, and in place of L, if we put pi, then we will have sine px only dx, where p is a positive integer or it may be a 0. Okay, p is a positive integer or it may be 0 also. So if it is the finite Fourier sine transform of the function fx, fs of, right, then we can also define the inverse Fourier sine transform, inverse finite Fourier sine transform. So inverse, if we are given this, then inverse finite Fourier sine transform of this function, which is nothing but this function, that is fsp. Okay. Let me write it again. FSP. Okay. Or you can also say FSP. Okay, we can define its inverse Fourier, finite Fourier sine transform of these functions, and we denote them by fx, because if we take the inverse of this expression, fs will go here and we are left with fx. So if we will get fx, the value of fx, which is fs inverse of fs bar p, or it is fs inverse of fsp. Okay. So the formula is, inversion formula for finite Fourier sine transform is given by fx is equal to 2 upon L in the interval 0 to L. This is for the interval 0 to L. P is equal to 1 to infinity FSP sine P pi x over L, where it is necessary to define what is FSP and in which interval its finite Fourier sine transform is given to us. So where FSP is the finite Fourier sine transform of the given function fx over the interval 0 to L. Okay. So this is how we define the finite Fourier sine transform. Remember that the function fx, whose finite Fourier sine transform is to be obtained, it should be defined in that interval, and it also satisfies the Dirichlet conditions in that interval. If it is so, then we define the finite Fourier sine transform of the function fx in this way. And if the interval is from 0 to pi, then we replace L by pi so that the formula will be fx sine px dx, where p is positive integer or it may be 0. So if we are given the finite Fourier sine transform of any function, then we can find its inverse finite Fourier sine transform. By doing so, we will obtain the function fx, whose finite Fourier sine transform is given to us. Okay. So let's see one example to understand the formula and the procedure of doing problems in this case. So we have to find finite Fourier sine transform of, say, fx is equal to, say, we are given 2x, where x is lying between 0 to 4. Okay. So we apply the formula of finite Fourier sine transform of any function fx is defined as integration 0 to L fx sine p pi x divided by L into dx, where L is equal to 4. Okay, when you compare this interval from 0 to L interval, the value of L will be 4 and the value of fx is 2x sine p pi x divided by 4 dx. So we integrate this by parts, taking this as first function and this as second function, So we will have first function into integration of second function cos p pi x divided by L, that is 4 here, whole divided by p pi upon 4. Okay, minus integration from 0 to 4, derivation of 2x is 2, and again we have this expression as it is here, cos p pi x divided by 4 over p pi 4 dx. Okay, so Fourier sine transform of the function fx, which is nothing but 2x, is it will be 8x minus 8x upon p pi cos p pi x over 4, and we have positive sign, but the integration of yeah, cos is positive, so we have positive sign here, and we have 8 over p pi, and integration of cos p pi x over 4 is sine p pi x over 4 over p pi over 4, and we apply the limit from 0 to 4. Let's again simplify it. 8x upon p pi cos p pi x over 4 plus it will be 32 upon p square pi square sine of p pi x over 4. So when we substitute 4 here, we will get cos p pi. Okay, and so it will be minus 34 over, oh sorry, it will be 32 over p pi into cos p pi plus 32 over p square pi square sine p pi, and at lower limit both will be 0. So because cos of if you remember, cos of n pi is minus 1 raised to the power n, and sine of n pi is always 0, where n is an integer, positive integer, right? So this value, this expression will be 0, and this expression we substitute minus 1 raised to the power p here. Okay, so this is the answer where p is positive integer, so you can write here p is equal to 1, 2, 3 and so on. Now we take the second example. Find finite Fourier Sine transform of fx is equal to x square, where x lies between 0 to pi. So again, we use the definition of finite Fourier sine transform of the given function fx is equal to integration 0 to pi, because we are given the interval 0 to pi. So we have 0 to pi limit, and we have here sine px dx. Okay. So let's substitute the value of fx, Fourier sine transform of the function x square is equal to integration 0 to pi x square sine of px dx. Okay, p is 1, 2, 3, and so on. So this is equal to first function into integration of second function minus differentiation of first function into integration of this function. I am doing the shortcut. This is minus sine px over p square. Then again we have positive sign and differentiation of this, which is 2, and integration of this, which is cos px over pq. Now we apply the limit. So it will be minus pi square cos p pi over p plus 2 pi sine p pi over p square and here we have plus 2 cos p pi over pq. At lower limit, these two will be 0 and this will left. So we have 2 upon pq. So cos p pi is minus 1 raised to the power p whole divided by p. It will be 0. 2 minus 1 raised to the power p whole divided by p cube. So we have it will be square, pi square minus 1 raised to the power p plus 1 over p plus 2 can be taken common, minus 1 raised to the power p minus 1 whole divided by p cube. This will be the answer. Okay. I hope you understand the lecture about finite Fourier sine transform of the given function, how it is obtained, how it is defined, and the function should satisfy what conditions so that we can find its finite Fourier sine transform. Okay, so if you like this lecture, you can press the like button and you can share it, and also you can subscribe my channel. If you had not subscribed it yet, please subscribe it, and thank you very much for watching the video.